right, guys, today we're talking about acid-base neutralization reactions and titration. All right. So for neutralization reactions, what we do is we take an acid and a base, and they react. If they react completely, leaving no excess reactants behind, the products are going to be salt plus water. So acid plus base, our reactants over here, are going to produce a salt plus water. And a salt means it's an ionic compound. And I'll show you an example. All right. So acids always start with an H, and some of our bases end in OH or have a hydroxide on them. So what's going to happen is the H from the acid and the OH from the base is going to produce water, H2O, HOH, making H2O. And then what's going to happen is the X and the Y are going to combine and create an ionic compound. Remember, ionic compounds are always metals and then the nonmetals. That's why the Y comes before the X. So here's a real world example. We have hydrochloric acid and sodium hydroxide. What's going to happen is hydrogen is going to bond with the hydroxide, making H2O. So that leaves us with sodium and chlorine, and sodium, chlorine come together to make sodium chloride. And so this is our balanced chemical equation. Here's another example. We have sulfuric acid and magnesium hydroxide coming together. So the hydrogen from sulfuric acid is going to combine with hydroxide from magnesium hydroxide, producing water. And magnesium will be left over to form a bond with sulfate. Magnesium is a +2, sulfate's a -2, so they're going to have a 1-to-1 ratio, so they cancel out, making MgSO4. And then we look at it, and we needed the 2 to balance it out. So complete neutralization is where all of the protons or all of the hydrogens from the acid leave and go to the base. So they're accepted by the base, right? So here we see some examples that you might see in some of your mastering. So we have nitric acid and potassium hydroxide. So what's going to be a product? Remember, acid plus base makes salt plus water. So water is going to be a product. So we're going to have H2O over here. And then the potassium is going to form a bond with NO3. Potassium as a +1, NO3 is a -1. We use our green periodic tables. So it's a 1-to-1 ratio. So it's going to produce KNO3. And then our last equation here, we have sulfuric acid reacting with sodium hydroxide. So remember, the hydrogen is going to bond with a hydroxide, making H2O. So therefore, we're left with sodium, or Na, and our sulfate, which is our SO4, -2, to combine. When sodium and sulfate come together, they have to crisscross their charges, and they come up with Na2SO4. And then we'd have to go through and we'd balance this. This one is not balanced. So to balance it, we would need a 2 in front of the NaOH, and then a 2 in front of the H2O, and that should be our answer. All right. So this is just some examples. So what would happen when we have potassium hydroxide and hydrochloric acid coming together? Acid plus base makes salt plus water. This would be our balanced chemical equation. Here we have magnesium hydroxide, our base, and then hydrobromic acid. Our acid here, we're going to form water, and then magnesium bromide, and that's a 1-to-2 ratio, and so we'd have to balance it out. Then equation number 3, sulfuric acid combining with lithium hydroxide acting as our base right here. We're going to make water because acid plus base makes water, and then lithium sulfate. And lithium sulfate is Li2SO4. And then balance it out. All right, so evidence from a neutralization reaction. It's going to be an exothermic reaction. Oh, I'm going to have to pause this. Oh, how do I pause it? There we go. So exothermic, so we're going to give off heat. Product is going to be a mixture. We can evaporate out the water. We'll be left over with the ionic compound. And then we could see a change in litmus or other indicators proving that it's neither acidic nor basic, and it would be neutral. So here we would have a strong acid, strong base reacting here. Hydrochloric acid, sodium hydroxide, and what's going to happen is we're going to watch it. We're adding universal indicator. Universal indicator gives you that rainbow effect. So if it's like red, orange, yellow, we have it on lower than 7. And so that's why we see here it's like more of a reddish color, kind of pink. And then on the other side, We're adding the universal indicator to the base. And basic, remember, we're closer to 14, so higher than 7, closer to 14, and that's going to be our purples and our blues. And that's why we see purple. And what happens when we mix the hydrochloric acid and the sodium hydroxide is we should make a salt plus water, so therefore the universal indicator turns green. Isn't that really cool? I like that. And then this is just a little video. I think it's cute. And then I'm going to give this to you later so that you can watch it on your own. And I'm going to keep going forward. All right, so single replacement reactions. So those were double replacement reactions. So single replacement reactions, the general format is an acid plus a metal will produce hydrogen gas. Remember, hydrogen is diatomic, and a metallic salt. So just an ionic compound again. Here's an example of a real world. So we have hydrochloric acid reacting with magnesium. So we put magnesium into hydrochloric acid. And what's going to happen, you're going to see those bubbles, and we test for our hydrogen gas, right? It's going to escape. And what's left over is magnesium chloride. So we take the hydrogen from the acid, turn it into H2, right? So that leaves this right here, this metal to react with the non-metal in, or the negative ion in the acid. So that's where we get the MgCl2. All right, so here's just some examples. So we have hydrosulfuric acid reacting with iron. In this case, we're going to act like iron has a +3 charge. So we're going to have H2 as a product, and then Fe with a +2 combining with S with a +3, S with a -2, crisscross, and we're going to get Fe2S3. Fe2S3. Okay, here we have hydrofluoric acid reacting with zinc. So if we predict the products, we produce hydrogen gas, H2, and then zinc would react with fluorine. Remember, zinc has a +2 charge, fluorine is a -1, and that's why we get ZnF2. Here we have hydrocyanic acid with reacting with potassium. Hydrogen's going to turn into that gas, H2, and then we're going to have potassium cyanide. All right, titrations. Let's talk about titrations. So titration is a lab procedure that's used to determine how many moles or what is the concentration of a solution. All right. So talking about concentration, we've already talked about it. Molarity is the number of moles that you have of a substance per liter. Number of moles per liter. Right? And that's molarity. Moles, if we rearrange the formula, we take the molarity times the volume in liters to get moles. All right, so in titrations, an acid and a base are mixed to determine when equal moles of a proton acceptor exist for the proton donors, right? Like what? What are we talking about here? All right, so it's just talking about the equivalency point. So at the equivalency point, that's reached when the moles of the acid are equal to the moles of the base. All right, it's just a fun lab that we would have done, and there's many different examples. It's kind of messy, and we have to clean the tables a lot. But you just see what's going on here. Starting point, we have an indicator in here of phenolphthalein, and we have either the acid or the base in this one, and the other one in this. And then we just add and add and add, and we're swirling and swirling. And then when one drop gives us this pale pink color, we know that we've reached our end point, right? If we add another drop, we went too far. So then you have to add, let's say this was the acid and this is the base, we'd have to add a drop of acid. And if we have a drop of acid and it turned into this clear color, and you're like, all right, now let's try one drop of base. And if it turned pink, then you're like, yes, this is the point where the moles of the acid equal the moles of the base. See, one drop of acid added, it's clear. One drop of base added is pink. So phenolphthalein, the indicator is either it's clear or it's pink. Pink indicates that it is on the basic pH scale. All right. Here's an example of a math problem that we would use with titration. So we'd have our hydrochloric acid reacting with sodium hydroxide to produce, again, our salt and our water. Right? If moles of the acid equal moles of the base, we can use this formula. The concentration times the volume of the acid will equal the concentration of the base times the volume of the base. All right, so it kind of looks like this. So concentration times volume equals concentration times volume. All right, so here's a sample problem that you might see. So if 15.7 milliliters, so that's a volume, of 0.15 molar concentration of hydrochloric acid, so that's the concentration, titrates to an end point, remember moles equals moles, with 23.4 milliliters, so volume of NaOH, that's the volume of the base. What is the concentration of NaOH? So here we have volume of acid, concentration of acid. Here in this blue area, we have our volume of the base, so we're left over trying to find MB. So here's our work. So 15.7 milliliters times 0.15 molar equals 23.4 milliliters times our concentration of our base. Solve for X, right? So we're going to divide 15.7 times 0.15 by 23.4 to get a value of 0.10 molar NaOH. Here's another example. So we have 10 ml sample of vinegar, right? And vinegar is an acid. It's a weak acid. It requires 11.10 milliliters of 0.748 molar sodium hydroxide in order to neutralize. What is the concentration of acetic acid in this vinegar? So we're just, again, the question's asking for what is the concentration. So it gives us a volume of the acid, and we don't know the concentration of the acid, so that's our X, equaling the volume of the base times the concentration of the base. All right, so that's this work here. So volume times concentration equals volume times concentration. So acid over here, base on the other side. So when we solve for MA, we get a concentration of 0.830 molar of our acetic acid. And there you have it, guys. I hope this has been beneficial. And just know that I miss you.